is our last speaker for the day, and he's a PhD student at the University of California in Santa Barbara, and he will be talking about a derivation of the Smarr formula for AdS black holes from an effective action. Thank you.
Okay. First of all, thank you very much for the opportunity to give a talk in this wonderful meeting. This is a solo project, though I'm using some techniques or some results here that I'm gonna use. That I study with other collaborators for other purposes. Okay. Oh, sorry, what happened here? Okay. So this is the outline. I'm gonna give first of all some motivations, then a review of the Smarr formula and perfect fluid. Then I'm gonna show you a generalized Euler equation coming from an effective action. Then I'm gonna apply this generalized Euler equation in a holographic fluid, basically dual to AdS Reissner-Nordström black hole. And then I'm gonna give some comments on standard black hole thermodynamics. Finally, some conclusions and future directions. So first of all, some context, gauge gravity duality. So this is the holographic principle state basically that a quantum theory of gravity is dual to a quantum theory without gravity, living in fewer dimensions. And the best known example is N=4 Mills with gauge group SUN and a tough coupling lambda that is dual to type 2B string theory in asymptotically AdS phi cross S phi spacetime. For today will be important the semi-classical gravity or semi-classical limit, which is mapped to a strongly interactive quantum system with a lot of degrees of freedom. Here I have the identification of parameters where n is the degrees of freedom of each point in the space-time. In the case of N=4 Mills is the rank of the group or the size of some matrix in the Joy representation. And it is matched or is with the quotient of the AdS radio and the L Planck. And also in this case, I ignoring sneaky correction, so the top coupling is also very large. In concrete, today we will need these entries for discussion of today. First of all, a global thermal equilibrium. Basically, it's the idea that eternal black holes are dual to thermal state in the field theory. And in particular, like the black hole thermodynamics is mapped to the thermodynamics of the strongly interacting field theory. Also, it will be important to distinguish between global thermal equilibrium and local thermal equilibrium. This is because the boundary stress tensor of AdS black holes take the form of a perfect fluid. In particular, a perfect fluid is some kind of local thermal equilibrium, and as a particular case, they have the global thermal equilibrium. So somehow you can recast, for instance, thermodynamics as a perfect fluid in the global equilibrium, if you want. Furthermore, also, if you want, you can add dissipation to really start to discuss about hydrodynamics, which is basically geometries that have a future event horizon, and they are dual to non-equilibrium states. So roughly speaking, the last 2 points are the foundation of fluid gravity duality. So the motivation of this project, the broad motivation is to build effective action for the ON² sector of gravity to compute quantum and thermal fluctuation and also to work out some RG flows. We will not discuss that precisely this today. We will focus on something more concrete, more particular. This effective action already exists for the case of perfect fluid that follows the Euler equation that I stated over here. In this case, these fluids are mapped to a space-time that have a future event horizon with a flat curvature. Basically, you can imagine that you have black brains or a space-time that evolves in time to black brains. That is normally the context where people in fluid gravity duality discuss. So the question is, what is the effective action for space-time that have a future event horizon with non-flat curvature, like for instance, spherical or hyperbolic horizons? In that case, as the Euler equation doesn't work. So I'm gonna see now. So the more concrete motivation is that in the context of AdS black hole, there is this Smarr formula. There is a relation among thermodynamic variables, and that basically replaces the Euler equation. So the goal is to build the effective action for perfect fluid that once it applies to a holographic fluid reproduces the Smarr formula. And a secondary motivation is that the Smarr formula is also like the key motivation of the proposal of standard black hole thermodynamics that argues that the central charge, defined like here, like basically the number of degrees of freedom of the field theory, is a thermodynamic variable. In this way, in this proposal, basically somehow the AdS radius can vary as if we're a thermodynamic variable. So I will see from my construction of this construction that is consistent with the Smarr formula, we will show that basically this proposal is consistent with fluid gravity duality. So basically, I'm going to state that the proposal of standard black hole thermodynamics is not correct. Okay. So let's first of all review what is the Smarr formula. So let's consider AdS Reissner-Nordström black hole in arbitrary dimensions. This is the metric, and this is the lat function. Here, I consider in the case where you can have a flat, a spherical, or a hyperbolic horizon that is parameterized by the factor k. That is 0 for a flat horizon, 1 for a spherical horizon, and -1 for hyperbolic horizon. Since this metric is in arbitrary dimensions, the physical energy M and the charge Q are related to the parameter of the metric in this way, with some factor of t, where AD is the area of the unit as d-dimensional sphere. You can go and evaluate the Euclidean on-shell action and to get the grand canonical free energy for this black hole. And then you use that on-shell value of the grand canonical ensemble, the grand canonical potential, and the definition of the grand canonical potential to deduce the Smarr formula, that this relation between thermodynamic variables. If you divide it by the volume and use the conformal equation state, you can recast the Smarr formula as follows. So it's basically the Euler equation plus a correction. Karsh and Brandon Robinson argues that this correction is basically a surface tension due to the fact that for instance, if you had a spherical black hole, it's mapped to the boundary space-time where the field theory lives, to having like a compact space. And because of that, you get like a surface tension term. This argument for Karsh is just based on thermodynamics arguments. So we will generalize these arguments for local thermal equilibrium. And this interpretation differs from the standard black hole thermodynamics interpretation. Okay. So then a small review of hydrodynamics. What you should know about this is basically hydrodynamics can be understood as a derivative expansion on top of a perfect fluid. In this sense, it's like the first well-known effective field theory. The equation of motion for hydrodynamics are the conservation of the stress tensor, and if you want charge, also the conservation of some current, plus constitutes relations to close the system of equations. So if you want to build an effective action for hydrodynamics, you need two ingredients, as any effective field theory. First of all, dynamical variables. In this case, they will be auxiliary fields that will allow you to describe the fluid properly. And you need auxiliary fields because the hydrodynamics equation are first order with respect to the hydrodynamics variables. So these auxiliary fields will make you transform this equation to second order, and in that way you can deduce a variational principle to infer what is this action. A second, you need symmetries in order to organize the possible terms that will appear in the effective action. So these are the dynamical variables. You have d-2 spatial scalar fields describing the fluid element, a temporal scalar field describing the internal clock of the fluid element, and also a scalar field bar phi associated with a U1 gauge field. If you want that these scalar fields describe the fluid, you need to impose the Common condition. It's basically the statement that if this sigma I and sigma 0 are describing like the coordinates where you are at rest in the fluid, you shouldn't see any motion. And this condition implies this other condition over here that is like basically the evolution along the time of the spatial scalar field is 0. From this common condition, you can start to deduce what are the symmetries that you need to deduce the effective action. So basically, the following transformation in the scalar fields are consistent with the common condition. So you can introduce an arbitrary function that depends only in the spatial scalar field for the sigma I, sigma naught, and bar phi. And in that way, you will preserve the common condition. So basically, these symmetries will be gauge symmetries that you can use to write down the effective action. Now, if you collect the temporal scalar field with the spatial scalar fields, you can describe a target space. This target space has the following isometries. These are the right isometries that are consistent with this transformation. Essentially, it's a degenerate matrix that have a 0 eigenvalue in the temporal direction, also a eigennormal vector. So here we have the following conditions. Sorry, the following ingredients. The dynamical variable for the effective action are basically Stokes fields. The symmetry of this action are gauge symmetries. So now the following step to really write down the effective action is say, okay, I'm gonna write down local thermodynamics variable that must be gauge invariant with respect to the diffeomorphisms of the target metrics, but also with respect to the diffeomorphisms of the physical metrics where the fluid is living on. So these are the gauge invariant quantities. First of all, the entropy density is defined as follows. Is the square root of the determinant of this combination over here, where G is the metric of is the target metrics. And then B is the definition over here. There is small g is the physical metrics, and there's some kind of field lines associated to the scalar fields. Nu is some possible boosts that you can introduce in the target metric if you want. Then the chemical potential associated with the U1 gauge symmetry is the following definition. Okay, and these two definitions are gauge invariant with respect to, as I said, diffeomorphism of the physical space-time, but also diffeomorphisms of the target metrics. So with these local thermodynamic variables, you can write down explicitly the effective action for perfect fluid that is consistent with the Euler equation. And this has done by Dubowski's son in like 10 years ago. And then nowadays, there are more formal construction using Stringer-Keldysh formalism and also superspace formalism and supersymmetry related to the some symmetry of the thermal circle done by Rangamani and Hong. Okay, so the only thing that I can do to generalize this construction is to add a new gauge invariant quantity, because I know what are the dynamical variables, I know what are the symmetries, and they are the correct ones. So the only thing is introduce an extra thermodynamic variable that makes the job. So there are many possibilities. Anything that can be write down as a gauge invariance. So the which one that works for my purposes is the following. So basically, I introduce a new thermodynamic variable that is local, y, that have as definition very similar to the chemical potential, but it's important that here the scalar field is in the temporal direction in the target metrics. In the previous case, bar phi is the Stokes field associated to the U1 gauge symmetry. So they are different, the definition are different. And then I'll say, okay, I'm gonna write down an effective action as 0 order in the velocity expansion as follows. That will depend on the entropy, on the chemical potential, and this new y variable. This action looks simple, but remember that this definition behind them, there are some metrics over here. So if I take the variation with respect to the physical metrics where the fluid is living on, I can compute the stress tensor, and you got the following expression. That is over here. And then if you compare with the perfect fluid stress tensor, you can read what is the pressure and what is the local energy density. But after this, you need to make sure that you satisfy all the standard thermodynamics relations. So, sorry. So if you work out the thermodynamics relation, you can compute what is the temperature. It will be related with this partial respect to entropy, and this new extra contribution with respect to what is chi. And also, you can deduce what is the local charge density. In this sense, let me go back here. It's very important to emphasize that basically this is an action, it's an affected action, but then chi is basically some new thermodynamic potential. Okay, that depends on these three variables. So given this relation, you can work out the following equation. That is a consequence of the affected action plus the standard thermodynamics relation that we know from undergrad. And you got a new Euler equation. So you see the first part is the standard results that maybe you saw in another place, but then you get an extra contribution that depend on the variable y and the partial derivative with respect to y of the pressure. So as already said, basically chi is a local thermodynamic potential that codify all the local thermodynamic equilibrium, basically, or the local thermodynamic event. It's very important to emphasize that this effective action works for any perfect fluid with any equation of states. At this point, I haven't not discussed at all gravity. This is just effective theory reasoning. I said, oh, what are the variable? What is the symmetries? I write down some effective action that is consistent with the symmetries. So and I am not assuming in particular conformal symmetry at all. The thing that here, from this effective field reasoning, I cannot deduce what is the meaning of the variable y straightforwardly. But then when apply this construction to holography, I will see that holography suggests that the new variable y is related to the curvature of the spatial section of the spacetime where the fluid is living on. Okay, but it's not something that on the effective field reasoning is telling me. It's something that holography is telling me. Okay, so now my claim is that this generalized Euler equation is basically the Smarr formula once I apply this construction to AdS black holes.
Robinson, you have 3 more minutes.
Okay. So the idea here is that I consider AdS Reissner-Nordström black hole, and then I choose the boundary matrix as follows, where omega is the conformal factor. I'm gonna pick some conformal factor that depends on the coordinates of the boundary space-time. Then I choose the embedding coordinates as the trivial one, such that the target matrix becomes this expression over here. That is basically the horizon matrix. From here, using the definition that I gave you before, I can compute the thermodynamics variables, the entropy, the variable y, and the chemical potential. It's very important that because I choose a boundary matrix that is curved and depends on time and the rest of the coordinates, these are local function of the boundary spacetime, not the usual thermodynamics variable. From here, I can deduce what is the effective action. In particular, I can deduce what is the thermodynamic potential chi that makes the job. And this is the expression over here. You can see that the new variable y is proportional with the factor k that is parameterizing the curvature of the horizon. If k is 0, I got the black brain and this disappear and I recover the standard Euler equation. But if k is different from 0, I'm gonna get this extra contribution. Remember that this thermodynamic potential chi codify all the thermal information of this holographic fluid. And it's just function of the mu, s, and y. G Newton and the radius of AdS spacetime are just mere parameters of this effective action. They are not thermodynamic variables. Then you can compute the rest of the thermodynamics variables using the definition that I gave you before. And in particular, you can see that the derivative of the pressure with respect to y is also proportional to k. So if k is 0, this term goes to 0. Finally, you can just use by simple algebra to check that the Euler equation plus this extra correction follows. And this is guaranteed by the construction from the very beginning. So because I introduced this Weil factor that has dependence on the boundary spacetime, this was in a very mild way out of the equilibrium. But you can pick a W, the conformal factor, proportional to the AdS radius, and then you recover the global thermal equilibrium, and you can recast this equation as the usual Smarr formula. So the point is that the Smarr formula fits naturally in the framework of AdS CFT. So maybe this is the last slide. Let me see the time. Okay, so a comment on standard black hole thermodynamics. So in this construction, the reasoning, the line of stuff was very simple. Using just effective field reasoning, basically I got the local version of the Smarr formula. In this construction, it's very clear that the thermodynamic variables are different from the parameter of a specific theory. In this context, G Newton and AdS radius. So these parameters are fixed because they are just parameters. And secondly, the third point is that perfect fluids require that standard thermodynamic variables become local function of the space-time. Certainly, like the new thermodynamic variable that standard black hole dynamic proposed, that is basically the number of degrees of freedom, cannot become a local function of the boundary space-time. The other point is that variation of the AdS radius are well understood in the context of holographic renormalization, where the number of degrees of freedom changes along of a flow in the space of theory. So the point is that hydrodynamics is something very different to renormalization groups. So in this sense, standard black hole thermodynamics cannot be right at all. Okay, so yeah, let me say finally, my future direction is this one. I gave you an effective field theory construction, but it will be nice to evaluate the Einstein-Hilbert action explicitly to see if I can reproduce the same thermodynamic potential. The other more important direction is, given this effective potential, maybe there is an energy flow that you can use to go from non-streamal fluid to near streamal fluid and see if you can recover the Schwarzschild action. Okay, so that's it.
Thank you very much. Thank you. Robinson.
Okay.
Okay, so Arpan Kundu, please.
I have this question. So since you told like these things are well understood from holographic RG perspective, so like I mean particularly for the flat Reissner-Nordström case, what will be happen?
Sorry, I didn't understand the question.
I mean for the flat limit Reissner-Nordström black hole.
Sorry, I
Like
don't.
so what is your comment about the like flat Reissner-Nordström black hole? Like you're telling that like the RG flow is well understood, like holographic RG.
Yeah. This is sorry. Do you mean the holographic RG flow?
Uh-huh.
I mean,
So no, I'm saying like for the flat Reissner-Nordström black hole, like so like you will understand the whole I mean hydrodynamics and all.
I don't understand your question.
Can you repeat your question, Arpan?
Okay, so my question is like do you understand the like fluid gravity correspondence for in the flat case?
In the flat case?
Yes, and because you told like I mean I know the holographic RG and like.
So what is the connection between the flat case and RG flows?
No, I think what he's asking, sorry, Arpan, correct me if I'm wrong, he's asking you about if there's something to say from the sort of the flat case in holography. And it's called flat holography. I think, is that what you're asking, Arpan?
Yes.
Yeah, I mean, in principle, what should happen here is that the metrics that I show you, the target metrics, basically the horizon metrics, there is a null surface. So you can say that there is a Caroline structure over there, or some kind of Caroline structure. But then if you try to do this in flat space-time, it will happen that also the physical space-time where the fluid is living is also Caroline. So it will be a map between null surface to a null surface. So in this sense, maybe these kind of techniques can be used to write down explicitly the effective action for a Caroline fluid. That's the idea.
Okay.
Thank you.
More questions for Robinson? No. Can I ask you one question? Is this so? You did the computation from sort of the effective field theory point of view. Is it related? And I guess it is to the computations that several authors have been doing about this generalization of thermodynamics variables, taking like the cosmological constant as the canonical conjugate of the pressure, and you do that in holography from the action point of view, but from the gravity side, and then you can compute things. Have you checked that or seen
I
anything
think
about it?
the problem is that my way of thinking about this is that each time that people discuss standard black hole thermodynamics, where the cosmological constant can take as a variation, you always use these techniques to compute charges. But here you are requiring something else. You are saying now you want those variables to become local function of the space-time. So you try to ask an extra requirement. And in that sense, standard black hole dynamics fails because it cannot happen that L can become a local function because it's mapped to the number of degrees of freedom. That is something that is at each point in the space-time in gauge gravity duality. So in that sense, it's very clear that these two hydrodynamics is not the same that RG flows, right? So there is something complete.
Thank you. Any more questions before we thank again Robinson and all the speakers for the day? No more questions? Sure. Okay. So let us thank again Robinson and all the speakers and